Uh, Dear students, welcome. Today we'll discuss partial derivatives. So what was the idea behind the derivative? So you had a function of y equals to f of x. So you had function of one variable. Your dy by dx measured how much did y change with respect to x. Yeah. Now, if you look at a function of two or more variables, let's look at function of two variables. So suppose this is your function z. Now you can basically see how much does z changes if you change in x, or how much does the z change corresponding to change only in y, or how much does z change with change in x and y both. All right. So there are many possibilities of changing the variables. But in our course, we are interested in the following. We'll be interested in how much, if we change one variable, how much does your function changes. And that means what? If you change one variable, you hold the other variables constant, and then you're trying to see how does your function changes. Okay. So let's motivate that by one example. So z equals to x squared plus y squared. So this is how the graph looks like. Now what you do is you cut a slice with y equals to 2. Okay, so the idea is you have, this is your y, here this is your x, and this thing is your z. And now you're taking a slice off like that. You cut a slice, and then when you cut a slice, you get a curve like this in y equals to 2. So then you look at it like that. So if you look at y equals to 2, essentially you're having y as fixed 2. So your function can be seen as a new function f. I mean, that's just an abuse of notation to use the same f, but these are different functions, and f of x becomes x squared plus 4, right? So you see, now it becomes reduces to a function of one variable. So now the slope of the surface in the direction of y equals to 2. So this is y equals to 2. And what is the slope of the tangent will be given by the slope of to this curve, or will be given by slope to this curve here, right? At various points. So we can generalize this to any line x equals to k or y equals to k, where k is the constant, all right? And in this case, you can see the slope of the tangent is going to be f prime x, which is 2x. So at any of these points, the slope is going to be 2x. Yeah. So in partial derivatives, what you do is say, suppose if you took x equals to 2, a constant, or sorry, y equals to 2, a constant, then you are fixing y equals to 2. So your y becomes like a fixed variable, all right? It doesn't changes at all. It becomes a constant. So we can define the partial derivatives in the following way. So by temporarily fixing holding x constant, we can compute the so-called partial derivative of z equals to f of y with respect to y. And similarly, by holding y equals to constant, we can compute the so-called partial derivative of z equals to f of x with respect to x. Now let's just write that mathematically. What does it mean? It means if you're changing, you're holding what? X as constant, right? So that means in your function, which was f of xy equals to z, in this function, you are holding x as constant, right? And you're allowed to change y. So it will be f of x y plus h minus f of y x y. So you see, you're allowing your y to change, but your x is constant, and then you let and divide by this guy. You let limit as h goes to 0, and this will be your partial derivative of your function f with respect to y. Yeah, it's very similar to recall in function of one variable, you had f prime x, which was dy by dx is going to be f of x plus h minus f of x over h, limit as h goes to 0. So similar setup here, but here you're treating x as a constant, so you get partial derivative of f with respect to y. So this is how you read it, partial derivative of f with respect to y. Now, similarly, you can define partial derivative of f with respect to x. In this case, you let x change, your y is fixed, and you take limit as h goes to 0. And if these limits exist, then we say the partial derivative of f with respect to x is this quantity, partial derivative of f with respect to y is this quantity here. Yeah. Now, the notations, there are various notations for the same thing. So partial derivative with respect to x can also be written as fx. Since you're doing the derivative at y, you can write it like that. This can also be written as partial derivative of f of xy with respect to x. This is also written as zx if your z equals to f of xy. This is a notation for a function. Can also be written as dou z by dou x, partial derivative of z with respect to x, or so these are the various notations for the same thing. Similar for partial derivative with respect to y, this can be written as f y of xy. So this denotes the partial derivative with respect to y by dou y of f of xy or z y or partial derivative of z with respect to y or yf. So these are all notation for the same things. And as you can see later on, different notations are useful at different times. Okay. Now, let's look at the following problem. So now, given function of two variables, f of xy equals to x squared minus xy plus y to the 5, find the partial derivative fx and fy. So now you want to compute fx, y. In this case, you're taking derivative with respect to x, your y is treated as a constant. You can think about as a fixed number. So derivative of x squared is 2x because we are taking derivative with respect to x, minus y is a constant, so it will come out, and derivative of x is 1, and derivative of y to the 5 is 0. Yeah. Similarly, what is fy of xy? In this case, we'll treat x as a constant and we'll differentiate with respect to y. So this is partial derivative of f with respect to y. So in this case, we'll have what? Derivative of x squared is 0 because we are differentiating with respect to y, right? X will come out as a constant. Derivative of y with respect to y is 1, and then plus. Derivative of y to the 5 is 5, y to the power 4, because the derivative is happening with respect to y. All right, so that takes care of the first part of the problem. Now, second part of the problem, calculate fx61 and interpret your results. So basically, you're computing the partial derivative with respect to x and then substituting x as 6 and y as 1. So let's see. So here, this will give us, so let's just fx of 61 is going to be in this equation here. When you compute fxy, you put x equals to 6 and y equals to 1. So you get 11. Similarly, fy of 61 is going to be x is 6, so minus 6, and y is 1. So 5, 1 to the power 4, which is going to be minus 6 plus 5, which is minus 1. So now let's calculate and interpret your results. So what does it mean by, what is the interpretation of this? So derivative is the rate of change, right? So fx61 equals to 11. This means what? This means that first of all, the derivative is positive. So the function is increasing, right? And the function is increasing at the rate of 11 in x direction at 0.61. So this is what, hence the f is increasing at the rate of 11 in the x direction at 6.1. Similarly, what will be the interpretation here? F is increasing at the rate of -1 in y direction at 6.1, or rate of -1 is same as saying decreasing at the rate of 1 x direction. So this is how you compute and interpret the partial derivatives. Okay. Now let's do some more problems. So here, so g of st equals to this. So let's compute partial derivative of this. So first order partial derivative means the first, so partial derivative of g with respect to s. When you're taking this, you have to treat t as a constant. However, you will still basically apply the chain rule and everything you have learned here. So now think about it as this whole square. So derivative of that is going to be 2 times s plus st square minus t cube, because derivative of x squared is 2x, right? So if you apply the chain rule, we get and multiplication of by dou s of the inside stuff, which is s plus st square minus t cube. So this is going to be 2s plus st minus t cube. What is partial derivative of this with respect to s? So derivative of s is 1. Derivative of s is again 1. T is constant, so t square. And derivative of minus t cube is 0 because there's no s in there. So this is a partial derivative with respect to s. Let's compute similarly partial derivative with respect to t. So we get this guy here. Again, the same thing. You have to use a quotient, sorry, a chain rule. So 2 times s plus st square minus t cube times dou t, or partial derivative d of s plus st square minus t cube. So we get 2s plus st square minus t cube. What is partial derivative of this with respect to t? It's 0. In this case, your s is a constant, it comes out. Derivative of t square with respect to t is 2t. And what is derivative of t cube with respect to t is 3t square. So these are your partial derivative with respect to s and with respect to t. All right. The other problems you can do in, and here are the solutions to that. Maybe if you want, we can do one more. Let's look at b. So we have pxy equals to ln of x plus y cube. So let's compute px of xy, which is same as partial derivative of p with respect to x. I'm using both the notations so that we get comfortable with it. This is going to be, so here this is function of x, this is also function of x. So two functions of x multiplied with each other, we have to use product rule. So x times partial derivative of ln x plus y cube plus ln x plus y cube times partial derivative of respect to x. Okay, so this is going to be x. Now what is the derivative of ln of something? Is 1 over that thing multiplied by partial derivative of inside with respect to x plus y cube. So I'm writing chain rule step by step, but once you get familiar with it, you can directly jump on to the final step. Now what is partial derivative of x with respect to x is 1. So now this will simplify as x over x plus y cube. Partial derivative of this with respect to x is 1 because partial derivative of y cube with respect to x is 0. Again, why? Because y is treated as a constant with respect to x, plus ln of x plus y. So this is a partial derivative with respect to x. And similarly, you can compute the partial derivative with respect to y. Okay, so this is how you would compute the partial derivatives. And these are called first order partial derivative. Why are they called first order partial derivative? Again, dy by dx is the first order derivative, right? First order. Then d square y by dx square is the second order derivative. Yeah, these are derivatives, not partial derivatives, because here you have y is a function of x. Here you have z is a function of xy, so we need partial derivatives. Okay, again. So coming back to the first order, so we have z. Let's take z equals to f of x, y, which is same as x square plus y square plus 2xy, suppose. Now, what is the partial derivative of z with respect to x? Is going to be, let me use both the notations. Again, derivative of x squared with respect to the x is going to be 2x. This is going to be 0. Derivative of this with respect to x is going to be 2y. Similarly, dou z by dou y, partial derivative of z with respect to y is going to be, again, I'm using this as a notation. I'm going to write, so 2y plus 2x. Now note that z, or partial derivative of z with respect to x, is also a function after all, isn't it? It's 2x plus 2y. So if it is a function, nothing is stopping us to take a derivative of it again. So you can take another derivative of this guy. So I'll write it as dou f by partial derivative with respect to x. Now I can do two things with it. I can also take partial derivative of this thing with respect to x. So if I take partial derivative of this thing with respect to x, what do I get? Derivative of 2x is 2, and this is 0. And this is written as second order partial derivative of f with respect to x. Similarly, I could have taken another partial derivative of this with respect to what? Y, because it's also a function of y. In that case, what would I get? I take derivative of this guy again, but with respect to y. So I get 2, because derivative of x is 0 with respect to y. Let me write down that intermediate step, so that of 2x plus 2y, which is going to be 2. And this can be written as y dou x, right? So this is how we can define the second order partial derivative. So in this case, you see, if a y is a function, f is a function of two variables, x and y, then we obtain 4 partial derivatives. So partial derivative, second order partial derivative of f with respect to x, which is partial derivative of dou f by partial derivative of f with respect to x, and you take another partial derivative of that, and so on and so forth. So you get this guy for this guy, this guy. Now let's go back and do this computation for here. So we now compute, we'll start with this one here now, and compute partial derivative of this with respect to y, and we got, this is 2y plus 2x, and that is going to be 2. And then we take the same guy and we take derivative of that with respect to, let's go back to this one and take derivative of that with respect to x. Of 2y plus 2x, which is going to be again 2. So well, all the partial derivatives are same, but then the question is dou square f by dou x dou y is same as, so if you take derivative with respect to y first and then with respect to x, or if you take derivative with respect to x and then with respect to y, are they equal? And the answer is they are not always equal, but if the second order partial derivative are continuous around AB, then these are equal, and that is called Clarets theorem. That fxyab is same as fyxab. Yeah. So what is fx? fxyab is a short for, you go in the other order, okay, and fyx is short for, so if you have x, then so in this case you'll go first y and then x. Okay, so this is the schematic of second order derivatives. So here you have f, Now, if you can take function with respect to derivative with respect to x, partial derivative with respect to y, you get fx, you get fy. Now, once you have this, you have again function of x and y. So you can choose to take derivative with respect to x. So you'll get fxx partial, or if you can take derivative with respect to y, you get fxy. Similarly, if you are along this path, you can take derivative with respect to x, you get fyx. And if you take partial derivative with respect to y, you get fyy. Okay, so let's do a problem here. So we have find the second order partial derivative for this function. So before we go for the second order partial derivative, let's first compute the first order partial derivative. So g of xy equals to e to the power x square y. So let's take the first or partial derivative. So I will write down all the notations. Generally, you can just write one notation and that's fine. That is going to be derivative of e to the x is e to the x. So e to the x square y times derivative of this with respect to y. Again, I'm employing the chain rule, and that is going to be e to the power x square y. Derivative of this with respect to x. So y is a constant, comes out. Derivative of x square with respect to x is 2x. So we get 2xy. Similarly, let's look at gy is partial derivative of this with respect to y. This is going to be the same, e to the y square times derivative of x square y with respect to y. Derivative of y is constant, x square is y is 1 and x square is a constant, so it comes out. So we get times x square comes out, y is a constant. So this is what you get. Now we have to compute the second order partial derivative. There are 4 of them. So let's say what is gxx? This is going to be 2x square. By definition, this is taking derivative of this guy. So I'm going for this one here and taking derivative of that with respect to x. So of e to the x square y times 2xy. Now note that this is a function of x and this is also a function of x. So a product rule comes into the picture. So this is going to be e to the x square y times dou by dou x of 2xy plus e to the power x, plus 2xy times partial derivative with respect to x of e to the x square y. Now this is going to be e to the x square y. What is derivative of 2xy with respect to x? Is going to be 2y plus 2xy. What is derivative of e to the x square y? Well, this we have already computed right here, derivative of this. So let's just plug that here. So we get this square e to the power x square. Okay, so I'm just plugging that thing from here. So this is partial derivative with respect of gxx. Now we have to compute the other ones. So let's compute gyy. That is same as y of this guy here, e to the x square y. So let me first write down the notation in case there's still some doubt. So we get this is going to be y of dou g by dou y. So that we have computed x square y times x square. Now x square is a constant, so it comes out. So x square times of e x square y, and that we have already computed here, isn't it? Because this with respect to y is already computed here. So that is going to be x square times x square. So x to the power 4 e to the power x square y. Now the other ones, x. Now note that this is the notation is written other way around. The idea is that it's first derivative with respect to, so right, so it's written in the opposite order. All right, so this goes first and then this goes second. First, second. All right, so this is first and this is second. So now we get this is same as partial derivative of this with respect to, so we get e to the x square y times x square, and we get that is going to be, again we have two functions of x, so we have using product rule, two functions of x multiplied together. This is going to be e to the x square y, so 2x derivative of x square is 2x, and I multiply that this guy plus x squared times, now derivative of this with respect to x is already computed earlier, so x square y times 2xy. Okay. Similarly, you can compute gyx, and you will see that gyx and gxy are same because this is a nice function. All right, so it happens very rarely, particularly when the second order derivatives, partial derivatives are not continuous around AB, then the Clarets theorem will not hold. But otherwise, the Clarets theorem always holds, right? So yeah, so it helps us to simplify the computation. Now, let's look at one of the application of the first and the second order partial derivatives. So that is called Cobb-Douglas production function. The idea is the following. So sometimes the production function or the yield, the amount output produced, depends on two or more inputs, which are technologically related, right? So it can happen that two things are related. So suppose, let's look at the example here. So the amount of objects or quantity you can produce will depend on the capital and the labor, right? Like say you want to open a firm, how much production output will be depends on how much laborers or how much of hours, working man force hours you have, plus how much money you are able to put in, right? So there are many variables, but we are here interested in a special kind where our output basically depends on uh, the two inputs. So what is our output function here? Output is the product amount of output, and the input is basically the number of person hours worked per year if you're doing the yearly output. And K is the real value of the capital, which can go towards machinery, equipment, buildings, etc. A is some total factor of productivity. It's called total productivity factor. And B and 1 minus B are output elasticities of labor and capital respectively. So these are some constants. All right. So let's look at it from the following perspective now. Y is a function, the output function is a function of labor hours per year, to K, which is the capital input. All right. So now we can ask the following question: what will dou y by dou L represent, or partial derivative of y with respect to L represent, or YL represent? So if you go back to your definitions or the ideas we had in calculus of one variable, this will represent how much does the y changes with change in L, with a change in L, and your K is constant, right? So this is what partial derivative means, right? So let's see. So partial derivative YL is called marginal productivity of labor. That's a name. And it measures the rate of change of production with respect to amount of money expended for labor when the level of capital expenditure is held fixed. That is not going to change. All right. So L is fixed. your L is sorry, expenditure is fixed. That means your K is fixed, your L is changing, and then you can talk about YL. And the name marginal comes from the marginal cost function, right? I mean, like the word marginal was used earlier in this course. What was marginal cost function? So marginal cost function was what? dC by dx, right? So same way. So marginal basically represents the derivative part of it. Similarly, you can have YK, which is the marginal productivity of capital, and measures the rate of change of production with respect to amount of change in what? In K, which is what? Change of amount of money expended for capital, and L remains constant. That means the level of labor expenditure is held fixed. Okay, so this is what YL and YK represent, and let's try to see a problem based on this. So let's see. So suppose a country's production can be described by YL comma K. So this is a function, production function, and it is given by 15 L to the power 1 over 3, K to the power 2 over 3, where L and K are known. L is the unit of labor and K is a unit of capital. Now, question is asking us, calculate the marginal productivity of labor and marginal productivity of capital. So marginal productivity of labor is going to be YL, which is dou Y by dou L, which is partial derivative of this with respect to L. So it's going to be 15. What is derivative of L to the power 1 over 3 is 1 by 3, L to the power 1 by 3 minus 1, so 2 by 3. K to the power 2 by 3 as it is because it's a constant. So this is the, right? Similarly, you have YK is partial derivative of Y with respect to K. Again, going back here, 15 constant comes out. L to the power 1 over 3 is a constant. What is derivative of K to the power 2 by 3 with respect to K? We're using power rule, right? So K 2 by 3, K to the power 2 by 3 minus 1, which is K to the power minus 1. So these are YL and YK, right? They can be simplified to be written like this, but this is good enough. Now, what is it asking us? Now it's asking us, the second part of the problem is evaluate YL and YK when L is 100 and K is 55 and interpret your result. So let's compute YL of at what? At 100 and 55. That is going to be 15 times 1 by 3, 100 to the power minus 2 by 3, 55 to the power 2 by 3. And when I plug it in my calculator, I see that this is roughly 3.36. Similarly, YK at 155 is going to be 15 L to the power 1 by 3, which is 100 to the power 1 by 3 times 2 by 3 times K, which is 55 to the power minus 1 by 3. And the answer turns out to be, after using a calculator, 2.21. So this is a computation of your marginal productivity of labor and marginal productivity of capital. Now let's try to interpret this result. So what is the meaning of this? Of course, we can compute it, but what does it mean? It means that if you have labor cost as 100 and capital as 55, then your YL is basically 3.36 and your YK is 12.21. So your YK is bigger than YL at 155. This means what? If you increase, so YK is bigger, right? That means change in YK is bigger. That means if you increase K at 155, your output productivity will be more than if you increase L or the labor, right? So that's what it means. So we represent the amount. So if we increase the amount spent on capital while keeping the amount spent on labor constant, the resulting productivity will be higher. all right, than if we increase the amount spent on labor instead. So it tells you which quantity to increase to give a bigger productivity, all right? So this is the idea behind it. Okay. So this is the marginal productivities. Okay, you can have more than two variables, but for now we are happy with two variables. Okay, so the next concept is about relative demand. Now, think about it in the following way. So you have commodities A and B. Say iPhone and iPhone cover. Yeah, and basically they have certain price, PA and PB. And again, as we were discussing earlier with calculus of one variable, so the price will determine the quantity demanded, all right? So these two quantities are closely related to each other. And suppose, so we can have their joint relative demand functions as QA, which is F of PA, PB. That means what? The quantity A demanded, right? For A, the quantity demanded depends on the price of A and B both, all right? So there are many quantities like that, right? And not only to two, you can have like three, PA, PB, PC, you have ABC commodities, all right? But let's just study for two variables. Similarly, you have QB, it could depend on price of A and price of B. Now I should use different functions, so I'll call it this as F, and I'll choose to call this as G. So PA is the unit price for commodity A, and PB is the unit price for commodity B, right? So now, so the relative demands of two commodities are termed competitive commodities if increase in price of one results in increase in the price of the other commodity, right? So such commodities are called competitive commodities. Okay, that's the definition. Like say, for example, bread and cereal, right? If the bread price goes up, then the cereal price will also go up, right? Similarly, beer and wine, right? So price of one goes up, yeah. So that is the idea. So in what will happen if I want to write it in terms of derivatives, what does it mean? All right. So we'll come to that in a minute. Similarly, a relative demand of two commodities are termed as complementary commodities if the increase in demand of one commodity results in increase in demand of other commodity and vice versa. All right. For example, hamburgers and buns, and what? Apple pie and ice cream, right? So both, apparently both are used in the same thing, all right? So if the demand of one increases, then the the demand of the other increases as well. And similarly, if hamburger demand increases, then the bun demand also increases. So here's a setup. So you have the things are competitive if you have what? If you have dou partial derivative of QA with respect to the price is increasing, so then such commodities are called competitive, right? So the idea is, let's go back. Why is it competitive? Because if increase in the price of one commodity results in increase in the demand for the other commodity, okay? So increasing the price results in increase in the demand of the other commodity, okay? So if you reframe that as a partial derivative, you have dou QA, a partial derivative of QA with respect to PB is greater than 0, and QB with respect to PA is greater than 0, then the commodities are basically competitive. Now let's read this again. What does it mean? It means that QA is, if PB is increasing, QA is also increasing. Or if QB is increasing, PA is increasing, then QB is also increasing. That's what it means by competitive, as mentioned here. Now, what does it mean by complementary? let's look at this. So QA is, so PB is increasing, then QA is decreasing. And if PA is increasing, then QB is decreasing. If that happens, then we say the commodities are complementary. So here's another example. So let's check. So retailer sells both raincoats and umbrellas. QA and QBB quantities of umbrella and raincoat demanded respectively, and they depend on price PA, which is the price of umbrella, and Q and raincoats price BPB. So price of PA is price of umbrella, and PB be the price of raincoats. So now we want to determine whether these commodities are competitive, complementary, or neither. So in that case, we have to compute. So we are already given QA function, take derivative of this with respect to PB. All right, so note that this cross QA, and then you're taking derivative with respect to price of B. Yeah, so this is about discussion of how commodity A, the demand of commodity A is changed by demand of price of commodity B. All right. So that's why you have Q on the top and the price in the bottom. All right. Because if you're discussing QA, then this becomes the usual marginal functions. All right. So we are interested in the cross of this, because they are jointly related now here. So now what is QA by P, dou partial derivative of QA with respect to PB. So here I want to take partial derivative of this guy with respect to PB. So everything is a constant except for, so they will come out, except derivative of this 2B with respect to B, which is going to be just 2. Similarly, let's look at this guy. So QB over partial derivative of QB with respect to PA. In this case also the bottom does not has PA in it, so it will come out, it's a constant times 1. Now, determine these quantities are complementary or so price is generally positive, right? I mean, like prices are positive all the time. So the price is positive means this part is positive. This plus adding 3 is also positive, multiplying by 3 is also positive. So this is going to be greater than 0. And this is also going to be greater than 0. That means what? These two these two products are what? They are competitive. All right. So thank you for your attention. That's it for today.